So it says find the area common to those two graphs. So like the overlap between them. You're going to have to be able to draw a graph. And I went back and rearranged these notes so we could practice drawing this because it seemed like that was an area where we needed more practice. So let's do the first one. I'm going to pick some values for theta to plug in, and we're going to do this -6 cosine theta. So let's start with 0. All right, so if we plug in 0, cosine of 0, 1 times -6 would be -6. So let's see where that is. It's a little tricky because it's negative. If you were to rotate to 0 pi, like you didn't go anywhere, that would be on this side. But we went 6 in the opposite direction. So that's going to put us right here. I don't have like any other, like I don't have a 3 or a 6 or a 2 in there. So I'd probably just go for the quadrant angles. Let's do pi over 2. Cosine pi over 2 is 0. And so where am I going to put my point? Yeah, well, and we call it the pole for this. If you say origin, I know what you mean, but technically it's the pole. All right, and then let's do pi. Cosine of pi would be -1 times -6 would be 6. Okay, so watch me point to this. If you rotate to pi, that's going to be over here. And if you go 6 in that direction, that's going to put you right here, back where you started. So, hey guys, if all we have are those 2 points and we went from there to there and then from there to there, what shape did we get? It's just a circle. Do your best to make it like circle-y, but that's all it's going to be. And actually, I'm going to try to color code mine. So when I post this, you'll be able to see it with different colors. Yeah, I said just do your best. Mine's not perfect either. It's okay. Like, there we go. See, look, mine's not perfect. It's good enough. Okay, now let's do the other one. So make yourself a table for the other one. And again, we'll just start at 0 pi. So if you plug in 0, cosine of 0 would be 1. And so what do you get out of the whole thing? 0, because it would be 2 minus 2, which would be 0. So you're going to start at the pole. Now, I knew that this first one was a circle, so I kind of let us off the hook with plugging in more numbers. We're going to need like a few extra points for this one to see what's going on. So I'm going to have us do pi over 3. The reason I picked pi over 3 is because it'll turn out nice. What's your cosine of pi over 3? 1/2. Half of 2 is 1, and then 2 minus 1 is 1. So pi over 3, 1. So watch me point to it. This little dotted line would be pi over 6. This one's pi over 3, and we're going to go 1 unit in that direction. So that's going to be right there. All right, then let's do pi over 2. Cosine pi over 2. 0, so what do you get out of the whole thing? 2. So pi over 2 would be up here, and we're going 2 in that direction. So let's just look at what we've got so far. We started at the pole. We're going to connect to here and then to here. So like that's what we have so far. So then let's do 2 pi over 3. Again, I'm just bringing that up so we get a few extra points like in here, so I don't skip too many. I didn't mind skipping them when it was a circle because that's just a circle, right? But I'm trying to get us a few more points here. So think about 2 pi over 3. That would be in the second quadrant. What would be cosine 2 pi over 3? Good. -1/2 times -2 would be +1. So what do you get out of the whole thing? 3. The negatives cancel. So -1/2 times -2 would be +1, and then +2 gives you 3. So watch me point to it. This line right here would be the 2 pi over 3, and we're going to go 3 in that direction, so that puts us right there. And so if you still are connecting this together, it's going to do something like that. And then let's do pi. So cosine of pi, -1 times -2 would be +2. So you get pho. So if you rotate to pi, that's going to be in a this way direction. And if you go 4 in the direction of pi, that's going to put you right here. So it's going to connect there. Now, I'm not going to make you plug in any more points because we should be able to keep it going. Just watch me point to this. We started at the pole. We went up here like this. It's going to keep going and come around again. Do you see what I'm saying? Like it's going to look like a heart. Like you can basically just keep that going. And like, I don't know, this isn't going to be perfect here. I'm going to try and just reflect these points. But they're actually called cardioids. You get what I'm saying? Like cardiac stuff, because it looks like a heart. Mathematicians are not very creative, so everything is like kind of what it looks like, just what it sounds like. All right, does yours look okay? I'm not grading your art skills, but are we like, all right? Okay, mine are green and pink. I know you can't really tell up there, but anyway, we got a picture. Good job, guys. Okay, that's the part I really wanted to focus on. Now it says find the area common to them. So do you see how that's going to be this section in here? Like where they both overlap? Okay, so do you see how this section right here is where you're under the pink graph, the one I have labeled pink, and then the rest of the section is under the green one. Are we seeing that? Because like, again, you're not sweeping left to right, you're rotating around. So do you see how if I rotate this way, that portion is under the pink one, like the circle? Yeah. And then if you keep going, you're under the green one. Okay, so let's do that portion for the pink one. It's going to be 1/2, and then whatever r is squared d theta. Which one was the pink one? Or the circle one? Which one was the circle one? Yeah, the -6 cosine theta. So as we rotate, let me see if I can zoom in with it. And also my picture isn't real great. They should intersect right there. It's just like my picture's not perfect. When I drew my circle, it didn't turn out perfect. Did you get what I'm saying? Okay, so as we rotate like this, and we want the part that's like common to both of them. Like what we're going to end up finding is this. Like we want the part that's inside both of them. But if you rotate, I can't like take my fingers off of my body to do this. If you rotate like this, for that first little section, you're just under the circle. And they should intersect perfectly there. Mine doesn't intersect perfectly because I'm not perfect. You know what I'm saying? Like it should intersect there, but we have that part is just under the pink graph. All right, so let's figure out what those boundaries would be. Let me go back to pointing to the graph. When we did 0 pi, we started here. With me? You kind of have to watch me point to it. This was where we started. 0 pi was here. And then when we came around to this point, that was pi over 2. So we're going to start at pi over 2. And then we're going to rotate to this point. Gosh, we are going to have to put that in the table. I was trying to save you some work. We are actually going to have to put that point for, or actually, no, we know where that is. What is that rotation to? Like on your unit circle? Yeah, good. That's 2 pi over 3. That's like where this is. We don't have to actually figure it out. It's just going to be 2 pi over 3. So from there to there. Plus, and now we're going to do another one for the other graph. And so that one was the 2 minus 2 cosine theta. Just set it up blank and then you can go back and fill it in. The boundaries are honestly the hardest part because the rest of it's just the formula. Like you just put all that in there. Getting the boundaries is the hardest part. So let's look at the green one. And again, you just need to watch me point to it. We started at 0. This one kind of makes a little bit more sense. 0, and then we went to pi over 3, and then to pi over 2. Oh, and here's where we're going to start. So we're going to start at 2 pi over 3, like where this one left off. And again, still watch me point to it. And we're going to rotate all the way to, where's here? Pi. So we're going to rotate from 2 pi over 3 to pi. Now, what we found with this is this area. Do you get what I'm saying? We found from here to here was under the circly one, and then from here to here was under the green one. But if we want the entire area, what do we have to do to that answer? Times it by 2. So if you multiply all this by 2, what's going to happen is, yeah, like the 1/2s are just going to cancel. So what I want you to do is go ahead and put that in your calculator. And again, what we found was the area from here to here. We just found like the top half of it, and then we're going to double it. It's like, do you remember the clover ones? If you wanted the whole thing, you would find one petal. You would just do one petal and then multiply it by however many petals you have, kind of a similar. So just don't type the 1/2. Okay, so we got 15.707. Yeah. Okay, let's try the next one. Write an integral for the area bounded below by this graph and then above by that one. All right, so let's draw a picture. You need to be able to draw this. Okay, it'll just be a quick sketch because it's just this one thing. Okay, so let's plug in some angles. Let's start with 0 pi. Sine of 0. 0. So you're going to start at the pole. I didn't put a grid on this one because it's just going to be a really quick sketch. And I think for all the others, you have a picture. Yeah, I gave you a picture for all the other ones. Or not, I didn't give them to you. Do you know where I got these problems from? All right, and then let's do pi over 2. Or actually, there's a 2 in there. If there's a 2 in there, what would we probably want to do? Okay, good. Pi over 4. Because if you plug that in, it's going to turn to pi over 2. Sine of pi over 2 is 1 times 8 is 8. So if you rotate to pi over 4, that's going to be like right in the middle. If you go 8 in that direction, I don't have this labeled. This is just to get a quick sketch. All right. And then if we do pi over 2, the 2's would cancel. You'd have sine of pi, which is 0. So what happens is you start at the pole, it comes out to here, and it goes back to the pole. So do you see how you have this leaf? And those ones are called the roses. Like they look like flowers. Okay. I think they look like clovers. I think they should be called the clovers, but whatever. The circles are going. Here, hold on. That's a really good question. So let me grab a different piece of paper for that. If you get a circle, it's going to be like one side will be at the origin, but you're going to have another point like on an axis. Does that make sense? Like that one was floating out in space. You won't get a circle. That's such a good question. You're the first person that ever asked me that. So you could have a circle like this, or you could have a circle like this. Do you get what I'm saying? But you won't have one that's like off center. Cool. All right. So we've got that. So it's bounded below by that and above by the line y equals 2x. All right. So that's just going to be a line that goes through that. Obviously, that's not to scale. But I just stuck a line with a slope of 2. So wait, which side of this do we want? Below by this thing and above by the line. So this is the area that we're trying to find. So go ahead and set it up blank. And nicely, this one just says write an integral. So once you set it up, you're done. You don't have to even put it in the calculator. It's bounded above by the line and below by the, I know that's confusing, right? It's bounded below by this curve. So that's the bottom one. And then above by the line. So the line is the top one. All right. And then in there, you're going to put 8 sine 2 theta. And the hardest part is finding the boundaries. And actually the first boundary is kind of easy because where are we going to start? Yeah, 0 pi, or even just 0. Here's the tricky part is you have to find this intersection, okay? And it comes back to like sine, cosine, tangent. I don't remember if you remember this from the very first day that I just showed you what polar equations were. And I said tangent inverse is going to come up a lot. Like tangent is y over x. Like if you have tangent of an angle, it's opposite over adjacent. Okay. I mean, it's just true. Tangent inverse does come up often with these. Okay. So you would have tangent of theta, and I'm just setting this up as a side problem, is y over x. It's just true because of SOHCAHTOA. So what does y equal for the line that they gave us? What did they say y equal? 2x. So this would be 2x over x. So it's just 2. And what we're looking for is the angle. So I want theta. Oh, this is kind of like the warm-up that we did. Remember we had to like anti-sine? So this is going to be tangent inverse, which of 2, which you could write with a little -1, or what's the other way you could write it because they mean the same thing? Arctangent, either way. Weirdly, that's your upper boundary, whatever that is. We don't have to put it in the calculator, but it's tangent inverse of 2. You do see a lot of tangent inverses in these because tangent is y over x, and then you have to inverse it to get the angle. So I guess the takeaway there is if you get a multiple choice question and you absolutely have no clue, pick the one with a tangent inverse in it because it comes up a lot, I guess is what I'm saying. Yeah, and that's all you had to do was set it up. So that's it. What is tangent inverse of 2? Now I'm curious. 1.107. But that's not in degrees, that's in radians. So anyway, for what it's worth, that's the answer. Write an integral. So again, we don't even have to work it out. Just write an integral that gives the total area enclosed by this thing. I would just do the top half and then take away the 1/2. Like if you double it, you just don't have to put the 1/2. Okay, so integral, what on earth is this thing? Sine squared theta. Just don't forget to square that again. So actually, if this was a multiple choice question, it would be sine to the 4th, okay? And again, like I keep saying, the hardest part is to figure out the boundaries. But if we're doing this first loop, it would start at 0 pi, good. And then look, if you rotate up to here, that like if you just wanted this part, that would be pi over 2. So if you keep going, it would be pi. So actually, let me just go ahead and bring this up because it's worth talking about. Let's say you did only do this section. Like, let's say you did 0 to pi over 2. Then you would just multiply it by 4. So there's like a lot of different options you have for ways you do this. And gosh, I love this graph. Isn't that so cool? All right, what is the area bounded by that awful thing? I mean, the equation's awful. The picture's cool, though. I like the picture. Isn't that neat? Neat. Get on board. Cool.
Yeah.
Okay, cool. So 1/2 integral, and then you're gonna, I'm just gonna write r squared d theta. R is this thing. I'm not recopying that. I would just write r squared d theta. And then what are your boundaries? What do you think? If we want the area of this whole thing. Good. Why is it 0 to 2 pi?
All the way around.
Or all the way around. Have fun typing it in, guys.
Just the not calculated. Yes.
I would go with B.
Well, or you could just type it in, guys.
No.
This wasn't actually a hard problem. I do too, but that's just because my name is Beth, so I always pick B. Like that's just my go-to answer.
It's like
And this one will think for a while.
where it said that what used to be C and then they call it all into it.
Yeah, the most common answer for college. On SAT setting.
Hmm.
It's like 30% of the time.
All right.
Did we get this? 3.632? Okay, let me just go ahead and say this because I did this yesterday just to check. If you forgot the squared, you would get this one. If you forgot the 1/2, forgot, can't write. If you forgot the 1/2, you would get this answer. And if you forgot both of the squared and the 1/2, you would get this answer. So it's very, very easy to get not the right answer.
I got none of those.
Okay, last one. This is cool. You've got this little like tiny piece in here and then the bigger one. So here, let me show you what would happen here. Where's the polar curve? I'm going to write it a little bit bigger because it's small here. It's theta cosine theta. Oh, and they gave us the derivative. That's cool. I don't know what we're going to need that for. I need to read the rest of it. But watch me point to this. You would start here and it's going to go around for this little loop. And then it's going to go around for the bigger loop. And if you kept it going, you would get an even bigger one. And then if you kept it going, you would get and then it keeps going around. Isn't that cool? Cool. Neat, guys. Get on board. Okay. So let's see what this is asking for. Find the area. Oh, you know what? I got this from a 3 response question and I just took part A from it. So I actually don't think we need this derivative at all. I think that would have been for part B or C or something. I just took part A because that pertained to what we were doing. So 1/2 integral, and then the whole thing squared. And like I keep saying, the hardest part is the boundaries. So we want just the little loop. So where would it start?
0 pi.
Get 0 pi. Now here's the thing, we're gonna have to do a little bit of work for this. You have to know at what amount of rotation does it come back. So how could you figure that out? You would take this equation and do what with it? I want to know when it gets back to the pole. Set it equal to 0. So we'll have theta cosine theta equals 0. And you're setting each one of these factors equal to 0. So the first one's theta equals 0, which obviously is where we started. The other one is cosine equals 0. And so what amounts of rotation would you get for that? Pi over 2 would be the first one, and so that's the one we need. But if you kept going, you'd have 3 pi over 2, and then 5 pi over 2, and 7 pi over 2. Like, it's going to keep going around and around and around. Have fun typing that in.
How did we figure out the theta?
Oh, that was given in the problem. I just wrote it bigger because it was so tiny, but they gave us that.
How do you know which one is great?
Oh, the theta cosine theta is the whole thing. Like that graph, like, do you know how the rows graphs, like they'll do this loop and this one and then it'll just keep going around like this. If you kept rotating, you would just keep getting that. This graph instead gives you a little loop and then it goes around like this and then it goes around like if you kept going, like that's all the same equation. Isn't that cool? Cool. It is, it's neat.
No, I think it's just laughing. Thanks.
It was a good question because it does look like it's 2 different graphs, but it's not. It's all the same graph.
That's what I said.
Are you making friends with your parentheses over here?
I got an answer, but I'm not sure.
The problem is when you hit cosine, it starts a parenthesis, so you have to end it. Well, here, can I color code these? Here, look it. So when you hit cosine, it starts a parenthesis that you have to end. But also, when you hit math 9, it starts a parenthesis that then ends. So there actually ends up being 3 sets of parentheses there. Oh, good. Okay, point 126.